conversation about polar and nonpolar molecules. Remember, the conversation on polar and nonpolar molecules is directly related to, but not the same thing as, polar and nonpolar bonds. We talked about polar and nonpolar bonds, and this text, unlike other chemistry texts, does not differentiate to a large degree the differences based upon the difference in their electronegativities. Let me go through and make sure. Yes, we are recording. So it doesn't go through and say, for example, we're looking at two atoms. We're going to look at their electronegativities. We're going to subtract them from each other to find the difference, and based upon that difference, decide whether or not this is a polar or nonpolar bond. This text kind of leaves it up to, hey, is it perfectly the same or not? And here's the deal. The difference between electronegativities of two elements, well, two elements are never going to have exactly the same electronegativity. So this textbook kind of sets it up that it either is or is not based upon are they the same or are they not. Other textbooks that you might have and look into would say, okay, if you have two elements and you find the difference between their electronegativities, if the difference between their electronegativities is within this range, it's nonpolar. Is it technically maybe just slightly polar? Yes, it is. But we're going to call this range nonpolar, and we're going to call everything above that range polar. So this text kind of makes it easier. It goes through and just says it either is or isn't. And oh, by the way, it isn't perfect. It is not a nonpolar, therefore it is polar, if the bond is between two elements that are not the same. Okay? That's kind of the way this reduces it down. Now remember, what we're going to look at is the individual bonds that make up a molecule, and then that's the question of polar-nonpolar bonds. And then we look at the arrangement of the polar or the nonpolar bonds in the molecule to figure out if it is a polar or nonpolar molecule. Two different questions. So I have on the board three different molecules from the text that they give us as examples to look at to figure out whether or not these molecules are polar or nonpolar. And the first thing we have to do is determine whether or not the bonds that make up each molecule are polar or nonpolar. All right, so let's do that. Three dimensionals, you guys should feel pretty comfortable looking at these now in 3 dimensions. This first one has arsenic and trichloride, okay, 3 chlorines around it. These are all covalent, right? So these are all using the mono, di, tri, tetra naming paradigm. So this is arsenic trichloride. Looking at this, pretty quickly see now that this is a pyramidal. Remember, you guys are working on this before the quiz, right? This is a pyramidal. It's a column 5 element, 3 attachment points, camera on the top, forms a tripod. It's a pyramidal with bond angles of 105 degrees. Is this based on a tetrahedron? Yes. Is it a tetrahedral? No. It's a pyramidal. Okay. So looking at this, the bond angles of 107 degrees apart, and we look at the electronegativity, we need to consider the electronegativity between chlorine and arsenic. 3 times, but the same difference, right? Looking over here at the periodic table, we're going to compare arsenic with chlorine. Comparing those two, which has a greater electronegativity? Chlorine. Remember the trend. Good. The trend is up and to the right. Which one is higher or much farther to the right? Between arsenic and chlorine, it's true in both cases. Chlorine is above and to the right of arsenic, so that it's pretty simple. Chlorine has a greater electronegativity. Because of chlorine's greater electronegativity, chlorine is exerting more force to get those shared electrons to be with them. It's not sharing fair with arsenic. Chlorine is going to pull those electrons towards itself. So how would I indicate that on this? I would go through and draw this directional symbol here saying the electrons, the electrons that are being shared with arsenic are still being shared, but they're going to tend to be with chlorine. And when they tend to be with chlorine, it's going to make the arsenic relatively positive. That happens in 3 cases. Okay? So you can see from here that the electrons that would be shared between arsenic and chlorine are going to tend to be with the chlorine. They're going to tend to be pulled away from the center, right? And we've got an unbonded pair on the top. So now we've looked at the bonds that make up the molecule. We've determined the polarity of the bonds. Now that we know the polarity of the bonds, we need to assess the polarity of the molecule. Remember, here's the deal. When you have a molecule, you've got things attached together. What we're now looking for is, we talked about how the molecules are made with symmetry, the symmetry of the atoms to form the molecule. Now we're talking about the symmetry of the forces acting on the molecule. Okay. If you see that there's a pull from this chlorine, and there's a pull from this chlorine, and there's a pull from this chlorine to form partial negatives, partial negative there, partial negative there, partial negative there. Okay? Are the forces that are acting on the center or pivot atom the same in all directions? Is the pull away from the center for these electrons, the pull away, is it evenly distributed throughout the entire molecule? What's happening on the top? Okay. Are the forces that are pulling the center, are they the same in all directions? If this were a perfect symmetry here, we would have a tetrahedral, right? We don't have a tetrahedral. We have a pyramidal. If, for example, this was an AsCl4 molecule, hypothetically, then we would have evenly distributed forces pulling in all directions, right? Then it would be perfect symmetry, and the molecule would not be polar. It'd be nonpolar. However, in this case, we have an unbonded pair, which is not changing. There is no pull from or away from this unbonded pair. We're having forces pulling electrons away down here, and down here, but not up there. And what that does is mess up the symmetry. You're going to end up drawing a line through the molecule and trying to find a place where you can draw a line where it's not symmetrical on both sides. If I go like this, the forces aren't symmetrical. I've got a pull, 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 and its own pair. If I had another chlorine up there pulling the same way, all 109 degrees apart, I could have symmetry. Because I can make one side have a different force on it than the other side, this molecule is not symmetrical with regard to forces, and therefore it's polar. It's polar. While these sides might be partial negative at times, the negativity of this side never changes. Okay, so because of that, this whole molecule is polar, and it has polar bonds in it. Okay. Looking at chlorine with fluorine. Here's another example. We have got a bond here, a bond here. We've got bonds obviously in these two directions as well. Looking at electronegativity, we need to understand the electronegativity difference between carbons in fluorine and carbons in chlorine. So carbon is here, fluorine is much farther to the right, and with chlorine, same case, it's one low, but it's much more to the right. So I'm going to submit to you in these two cases that the electronegativity is going to pull the electrons away from the carbon in all four directions. So there's going to be and again, because it's 3 dimensions, I draw the symbol beside it. In 2 dimensions, I would draw it over top of the bond. So here we've got carbon, is giving up it tends to be with fluorine. Carbon tends to lose the electron. Fluorine doesn't share fair, it's hogging the electron. In the same way, chlorine here hogs the electron, chlorine here hogs the electron, and chlorine here hogs the electron. Okay? So there are forces pulling the electrons away from the central carbon. Carbon will tend not to have electrons. Those valence shell will tend to be stripped because the tendency will be for the shared electron to be at chlorine, at chlorine, at chlorine, and at fluorine. Now in this case, are the forces perfectly symmetrical with regard to the directions they're pulling from? Is there perfect symmetry here? I submit to you, yes, there is. There's perfect symmetry with regard to the directions of the pull, but not to the magnitude of the pull. Here's what I mean. This is a tetrahedral, right? A tetrahedral is the shape that is formed because the bond angles are all perfectly 109 degrees apart in all directions. So we have perfect symmetry with regard to the forces pulling the electrons away from the central atom. Here's the shortcut way of thinking. If you have a shape that is based upon a tetrahedron, for it to be nonpolar, it at least has to be a tetrahedral. If it's a pyramidal, or if it is a bent, it has to be a polar. It will be polar if it's based upon a tetrahedron and is not a tetrahedral. Everybody got that? If the shape is based upon a tetrahedron and the shape is not a tetrahedral, it's polar. The only way it can be nonpolar is if it is based on a tetrahedron and it is a tetrahedral. Now, so we've got hope for this molecule. It's based upon a tetrahedron and it is a tetrahedral. Now here's the next kicker. It has to be if it's based upon a tetrahedron, it has to be a tetrahedral, and the way this text does it, every external element has to be the same. Right? Because here, it's based upon a tetrahedron. It is a tetrahedral, so we're getting kind of excited. This might actually be a nonpolar molecule. However, what is the force exerted between carbon and fluorine as compared to carbon and chlorine? Well, fluorine has a greater electronegativity than chlorine does, right? Fluorine has a greater pull in this direction than any of these do in any other directions, which means, though it's slight, this point here, this partial negative, this partial negative, this partial negative, and this partial negative, all around the central positive, this partial negative is stronger partial negative than these partial negatives. Fluorine is going to tend to have the electron more often than chlorine does. Okay? So fluorine is going to tend to be partially negative in a stronger way than any other of the chlorines, which means that even though this is based on a tetrahedron and it is a tetrahedral, the forces pulling in all the different directions are not equal, and therefore it is also a polar molecule. It's polar. So this is polar because it has an unbonded pair. This is polar because it has an unequal force of electronegativity differences, with the fluorine being stronger. According to this text, the only way this would be a nonpolar is if this were a chlorine. If I replace that with a chlorine, now what's happened? Remember, chlorine and fluorine have the same valence, so they're going to have the same role, the same place. They're going to look functionally the same. However, now that that's a chlorine rather than a fluorine, it has the same electronegativity in every direction, which means it has the same pull in every direction. So I've got equally distributed angles and equal amounts of pull. So now this is a nonpolar molecule. A CCl4 is not polar because the direction and force of all the vectors equal 0. They all cancel each other out. When I had it in the original form with a fluorine, the fluorine vector pulls more than the chlorines, and that makes fluorine tend to be more negative than the chlorines, which means the whole molecule now has a pull. It's a dipolar molecule because of the difference between the bond strengths. Okay? This is going to take a little bit of time, but it'll start making more sense as we go through it, which is why we've got to start going through it like we did with the polyatomic ions. We've got to just start practicing and getting comfortable and confident with it before we take the module exam. Okay? So, direction, two things are involved in vectors, the direction and the magnitude. The magnitude is called the scalar quantity. Maybe you've had this. If not, you'll get it in physics next year. Okay? So the scalar amount, how strong it is an indicator of the strength. It doesn't care about the direction. The direction is what sets those scalars either in complement or contrast to one another, either build or take away. What I'll submit to you is, if this were a chlorine, all these vectors, if we added them up, they would equal 0, which would mean that there is no net pull, or net pull on this, so there is no net pull. However, fluorine is different than chlorine, and if I were to add up all the vectors, there is a tendency for the electrons to be towards the fluorine. And since there's that tendency for them not to be equal, but to be towards the fluorine, this whole molecule now has a pull. Let's consider the last molecule they use. Consider the differences in electronegativity. We're struck, first of all, with this double bond between the carbons. What is the net pull here? Is there a pull? Carbon-to-carbon bond. Is there a pull? In other words, is there a difference? Is one carbon stronger than the other carbon? No. So these carbons are sharing these 4 electrons perfectly with regard to this bond. Now the question is, what is the relationship between carbon and fluorine? Again, periodic table, fluorine is much farther to the right than carbon. Fluorine has a greater electronegativity. Therefore, it hogs the electrons. It has more strength to grab and steal. So the tendency is going to be, in this case, since there are no bonds coming in or out of the board, I draw right over top of the bonds. And I'm going to say, okay, the tendency is going to be for that electron to be there, for that electron to be there, for that electron to be there, and for that electron to be there. That's my tendency, right? Now, looking at this molecule, and it's not as simple as what is the shape, because there is no single central pivot atom, right? There are basically 2 atoms here. Or these 2 atoms are forming kind of the center, the hub, if you will. So now let's look at the forces. What is the angle, do you think, between those 2 bonds? Well, considering that there are 1, 2, 3 attachment points around the carbon, let's speculate. What do you think it would be? 120 degrees, right? And this is 120 degrees. 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 So I've got all these forces acting around these carbons, but they're pulling symmetrically. As a matter of fact, I would argue that from the center point, this is kind of canceled out by this, and this is canceled out by this. You see that? See the symmetry around it? For every pull up, there's a pull down. For every pull right, there's an equal pull left. Do the fluorines pull on the carbons, the electrons from the carbons? Yes, they do. But they cancel each other out. And this perfect symmetry, I can't draw a line and say, that goes through the center and say, okay, this side is more negative than that side, or this side is more negative than that side. The perfect symmetry of it says, yes, there are forces at play, but in much the same way as we said, everything has charges, and if there's positive charges and negative charges, but the whole thing is neutral if they balance each other out, in the same way here, the forces that pull up have something equal pulling down, and the forces that pull right have an equal force that's pulling left. And so because the forces are perfectly balanced and matched here in this molecule is nonpolar. It doesn't have a pole because the forces acting on it are opposites and equal. There's a symmetry about the forces. And so this arsenic trichloride, this would be polar. Why? Because I can recognize an imbalance going through the center. Here, I can recognize an imbalance just even there, going through the center. This is polar. This one here, because it's perfectly symmetrical, is nonpolar. And here's one of the beauties about polar and nonpolar. This concludes the content for the module, but we're going to spend a few days working on this before we start doing review problems and practice problems, okay? Here's the beauty or the cool thing about polar and nonpolar is we're going to learn later. Actually, you're learning it right now. Here it is. Here's the deal right now. Polar and nonpolar. We talk about solvents and solutes. We can talk about 2 different liquids. I like to use, for example, water and oil. Okay? What we're going to learn is that polar dissolves polar and ionic. And nonpolar dissolves nonpolar. What do I mean? If I bring 2 things together and they are both nonpolar, they'll mix. And I'll come up with a solution that's homogeneous. But if I bring a polar and a nonpolar together, they're not going to mix. They're going to stay separate. Now, one of the reasons why we put oil and vinegar together and we shake it up, right? Why do we have to shake it up? Because they'll naturally separate. Why don't they just mix together? We're going to find that water is polar and the oil is nonpolar. And because of their polarities, they can't mix.